of finite point method to solution of hydrodynamics equation for metal casting and metallurgy applications. Felix Saucedo is a full professor at the University of Mexico, and he is interested in collaboration with our group in development of open source software. So I think we will organize our meeting as follows. First, we will listen to the presentation. This will be for maybe 30 minutes. After that, we can ask some questions. And then I can share email of presenter with you if you will have other ideas about how to cooperate, how to collaborate with Professor Saucedo. So Felix, can you hear me? Felix?
Yes, I can hear you. So
can you share your presentation?
Yes.
Okay, good.
Yes. So
Felix,
thank you.
Usually presentations on our seminars last for 30 or 40 minutes, and then we will ask you questions.
Okay, perfect. Then I will start. So thank you, everybody, and good afternoon. I will speak my presentation entitled A Meshfree Formulation for the Computer Simulation of Industrial Processes Involving Complex Flows. This focused to the casting application. The contents of this presentation are the following. I will start with the motivation of the modeling of this problem and with Meshfree methods. I will speak briefly about numerical techniques. Then I will present the governing equation and the numerics behind the finite point set method that will be used. Then I will speak also briefly about computational implementation, followed by numerical examples, and in the last part I will give some conclusions. So the motivation of this modeling is the developing of a modeling computational tool for the casting processes, since they are one of the most widely used techniques to mass produce metal products for different applications. These processes begin with a step corresponding to a mold filling, in which molten metal is poured into a water-cooled mold, where heat from the nearby metal to the mold walls is extracted, causing its solidifications. So in order to get homogeneous casting products, it's necessary to know and control all the physical phenomena involved in the process, as heat transfer, solidification, fluid flows, and also thermomechanical processes with the process parameters as cooling rates, inlet velocities, and the casting temperature. However, it's very difficult to improve these processes using experimental techniques because it's difficult to measure velocities, temperature during this filling. Therefore, numerical simulation is commonly used because they provide a large amount of information that cannot be obtained with other kind of methods. There are some traditional numerical techniques, mesh-based as finite element method, finite volume method, and finite difference method that have been used to analyze these kind of processes. However, recently, the mesh-free formulation is deemed as an alternative to these mesh-based methods because they provide some advantages over mesh-based methods. For example, they use a set of nodes scattered on the problem domain as well as its boundaries to represent the problem domain and its boundaries without requiring any information about the relationships between the nodes, so they do not form an element bench, which leads to model discontinuities, deformation, and some complex behaviors without the use of remeshing approaches. A truly mesh-free generalized finite differences method is the so-called finite points method. It has proven to be far superior to many other mesh-based methods and many other mesh-free formulation to treat problems in fluid mechanics. Especially, for example, for the automotive applications where it was continuously developed and investigated in the Fraunhofer Institute in Germany, where his creator, Dr. Jörg Kuhner, works, and where I have the opportunity to study and to learn this method. So in this video, we can see some of the results of this automotive application. For example, in the tank filling for a car, and also we will see in few seconds another more difficult application. For example, the crossing of a car in a water channel. So these results of real applications in automotive industry have been the part of the motivation to use this method in the casting industry. This is because clearly this method is able to handle high deformation in these flows, in these fluids, something that is difficult to carry out with mesh-based methods, and of course with other mesh-free formulation as smoothed particle hydrodynamics, because they have some inconsistencies and need some special treatments for the boundary conditions. So these numerical examples show this excellent behavior of finite point set method. So the governing equations for the mold filling step in casting are the Navier-Stokes equation in Lagrangian form, which are written like this. And the problem of free surface is completed with proper boundary and initial conditions. So here the d omega indicates the kind of boundary. 1 and 2 indicates a solid walls boundary, while the 3 indicates the free surface, the free surface boundary. To solve these incompressible Navier-Stokes equations, we have two choices. We can use couplet formulation and projection methods. Solving the problem with couplet formulation means that we need to compute simultaneously the velocity and the pressure files, leading to a high computational effort to get these two files in one step. So projection methods are used to decouple this file and to decrease the computational effort, leading to some set of steps where the velocity and the pressure are computed in a splitted way. So for this research, we consider a semi-implicit Chorin-Usawa's projection methods of 5 steps. So the 1, the 4, and the 5th steps are only the update of, for example, the particle's position, the velocity file, and the pressure file. And the real problems to get the velocity and the pressure are the second and the third steps. The second, we have an elliptic vector problem for the velocity, and in the third step, we have a pressure Poisson equation for an auxiliary or artificial pressure. So we can summarize that we are interested in solving the second and the third steps of this numerical scheme using FBM. And for that, we discretize the problem domain with a set of nodes as it is shown in this figure. So suppose that we are interested, for example, in computing the auxiliary pressure at the red point. And for that, we need first to define the neighborhood of this red point. So the neighborhood is defined through a weight function of Gaussian form that contains a variable named the smoothing length h, which defines the size of this neighborhood, and also we have an alpha variable that defines the weight that every neighbor particle will have with respect to the red point. So when we define this neighborhood for the red particle, we approximate then the auxiliary pressure phi through a Taylor series expansion of this variable around a neighbor position I, as it is shown in the figure, and as it is shown in this equation. When we have this approximation through the Taylor series expansion, we have these unknowns variables phis in terms of finite differences that are known, and the truncation error. We can repeat this idea for all the neighbor particles in the neighborhood of the red point to get a linear system of n equation for the n neighbor particles. However, we see from the third step that this phi variable also need to satisfy the pressure Poisson problem. So we must add this equation to this local linear system for the red point, which could be rewritten in matrix format as it is shown in this next equation. This matrix form is written for the truncation error, where the M matrix contains the spatial finite differences. The vector A contains the unknowns for the pressure at the red point, and the vector B are also the unknown pressures, but in the neighbor particles. Once we minimize the truncation error using the weighted least squares method, we get this system for the unknowns at the red points, where the new matrix W contains the value of the weight function in each neighbor particles. However, only we need the first element in the vector A to know the value of this artificial pressure. Therefore, we can work out the terms in this vector to get a global sparse system for all the pressures in the domain, which get this form, where the matrix K is a sparse matrix. Phi vector is the vector containing all the pressures, and F are also another vector containing the boundary conditions. Similarly, for the computation of the second step, the vector problem for the velocity, it is possible to construct a similar approach, where we define a new M prima matrix in this form, with the matrices C are zero matrices, and the matrices Y contains the boundary conditions for the velocity problem. Once we minimize this truncation error now for the couplet problem for the velocity, we get exactly the same form for the unknowns vector that now contains the velocity in h coordinate as it is indicated in this equation. Again, after working out the terms in this vector A, we can get a sparse system for all the velocities, for all the components in the problem with exactly the same form. So once we know some details about how to solve this problem with FBM, we can test this formulation with some benchmark example. But before that, we will need some pre-processing and post-processing tools to implement these benchmark examples more easily. So this formulation was developed in an in-house code written in C++, and this pre-processing and post-processing tools refers to, for example, the tool to incorporate the geometric models and to discretize these geometric models. And for example, the post-processing tool refer to the tools for the visualization that were prepared in BTK and Insight format for visualize the results in ParaView suite. And further, basic
Excuse me,
graphical.
can I ask the question now, or it's better later, about the preceding slides about the procedure? Because now you will talk about implementation already. Yes.
Yes. Sure. You can speak now. You can
because
make a question.
Maybe I just missed something, because you talked about interpolation. Yes, when you showed the slide with many points. It was about interpolation, yes? What,
yes, it was about interpolation.
No, where you have expression for phi or something.
This one.
But what is the connection when you, after that, when you talk about the matrix form, it's not only interpolation, it's some connection with Poisson equation, yes, for pressure. So
yes.
What is, how they are combined? So here, the expression is just for interpolation, yes? It's
yes.
Without any physics, just you have values in some points and you interpolate them in some red point, yes?
Yes, that is true.
And what is connection with the procedure of solving the equations? So I just missed, maybe it's...
Yes. So we have this interpolation equation for phi, and also the spatial derivatives of phi in this red point, in terms of this phi in the blue point, for example. So we can repeat this interpolation for all the particles that are inside the neighborhood of the red point. So in this linear system, as you correctly point out, we only interpolate the values. So to in this case include the physics that is the pressure Poisson equation, we need to add this constraint to this interpolation that we have here in the Taylor series, in the Taylor series expansion. So we have this, for example, n equation for the n neighbors, and we add one more equation that is the constraint over the pressure, that is the pressure Poisson equation. We can then with this n plus 1 equation, we can go to the truncation error that is the property that we want to minimize in this step. So this equation contains in the matrix M these spatial finite differences from the interpolation equations, but also one row in this equation contains this constraint of the pressure Poisson equation. So when we minimize this truncation error, we truncate the error taking into account the interpolation between the particles, but also taking into account the constraint of the pressure Poisson equation. So this is the idea.
Okay, thank you. And the sum is over all the points in this expression,
yes.
all the points in the domain.
This expression that we have here is for all the points in the neighborhood. So all the points that are
neighborhood. So you
yes.
somehow you define what is neighborhood, yes?
Yes, through
okay.
this which is the name in English?
Okay,
this
thank
Gaussian
you.
function. Yes.
Thank you.
Okay, you're welcome. So we was here, yes. So we prepare some pre-processing and post-processing tools for this problem to prepare the discretization of the geometrical model, and also to prepare the visualization of the results. Next, we also prepare a basic graphical user interface, also in C++, through the WX widgets library, only to make easier the task of simulation with this approach. So once we have all these details about the theoretical basis and also the numerical implementation in C++, it is time to go to the numerical examples. So the first numerical benchmark example that we considered here corresponds to the filling of the classical circular mold with core, because a lot of numerical and some experimental results are available in the literature, so we can directly compare with these results. Here in this slide, we can compare the results from the FPM formulation with the experimental results from Schmidt and Klein, where we can see that these numerical results match very well with the experimental counterparts in the free surface patterns and also in the domain evolution over time. We can see this complete filling in this video that we are showing here, where we can also see and appreciate that the numerical simulation remains stable during the wall simulation. So we can test also this simulation tool with more realistic examples. For example, this example we are looking in this slide, in this slide correspond to the filling of a simplified model of an aluminum alloy car rim. This simulation results show the suitability of this mesh-free formulation to model this filling process because the filling pattern evolution is quite smooth and it is clearly able to handle high deformation in the domain. For example, also the collision and the split of liquid fronts. And we can also verify these results with a second realistic simulation. For example, in this case, we are consider the filling of a machine component where we can also observe the robustness of this approach because we can see that we are able to model the splashing, the fluid fragmentation, the jets formation, and also the collisions between fronts with a good reproduction. We can observe further this behavior in a third real example corresponding to a water pump cover where this phenomenon also occur. So all these results show the suitability and feasibility of this FDM formulation to model free surface flows in casting processes. But as we know from the process, casting processes not only have a free surface fluid flow step, whilst they have a free surface fluid flow coupled with some heat transfer and solidification. So we need to take into account this coupling with the free surface fluid flow. Therefore, the heat transfer equation with the Boussinesq approximation can be coupled in the free surface formulation presented previously, following the same idea for solving the second step for the pressure Poisson equation. So once we have this coupling in the formulation, we can validate this implementation with the simulation also of a benchmark problem corresponding to a thermal flow in a squared cavity driven by natural convection produced by a temperature differences in opposite sides of this square cavity. The differences between the temperature are shown in this numerical setup, where if we consider that the melting temperature of the material in this simulation is between these two temperatures, a phase change will occur during the simulation. So this problem was also chosen because it is a popular example for testing numerical procedures that will be used for simulate this kind of couplet phenomenon. And the result of this simulation for the velocity field are shown in this video. We can compare these results with some results in the literature. For example, in this slide, we compare the velocity magnitude calculated with this FPM formulation with the numerical examples studied by Usmani and collaborators using finite element method. We can see here that the velocity, the maximum velocity and the velocity behavior match very well. So we can say that FPM is able to model this kind of processes correctly. We can also see this comparison with the temperature, and we can observe exactly the same behavior. So given these results, we can apply then these approaches to simulate our problem of casting. So in this slide, we incorporate the coupling with heat transfer and solidification in the classical benchmark example for free surface flow of the classical circular mold with core. Here is shown that the temperature evolution is very reasonable and stable during the evolution of the domain, and the cooling behavior is gradually reaching a stationary temperature which distributes in an homogeneous manner in the entire fluid inside the mold. While the temperature values at the fluid in the mold boundaries always obey and keep the prescribed boundary conditions. So with these results, we can then add the effects of solidifications. When we add these effects on solidification, we can see that the flow regime and also the flow pattern change completely when compared with the results without these solidification effects. So we can say that this solidification and cooling effects needs to be correctly modeled during the filling steps, because they change more or less the expected behaviors. However, it will be necessary to have more experimental and also more analytic and information to determine the accuracy and suitability of this FPM formulation and many other formulation for these free surface flow problems coupled with heat transfer and solidification, because no information is available nowadays in the literature for this kind of problem. So as conclusions of this work, we can say that FPM is suitable and feasible for the modeling and simulation of these processes in casting, because clearly it is able to reproduce all the complex phenomena observed in these processes. It is stable and has enough accuracy to capture all these physics involved in all the problems that occur during this processing, without needing any additional treatments, as for example remeshing approaches, or for example some stabilization algorithms. So also its numerical implementation is simpler than other mesh-based methods and other mesh-free methods, and by these reasons, it has a great potential for other applications and for other unexplored problems at the moment. So thank you to all the audience, and if you have any questions, I will be happy to answer them. Thank you.
Thank you, Felix. Can I ask you first question?
Yes, sure.
Do I get it wrong? Do I get it right? That points are steady state. So they don't move while solution evolves.
Where is?
Does points in your method are steady state? They don't move with solution.
Yes, steady. Well, I modeled these problems in the Lagrangian form. So we have here some points that are solidified, so they don't move because the solution is a solid state, as you say. But the liquid part of the domain needs to move because of the Lagrangian scheme.
Okay. Okay. Thank you.
You're welcome.
More questions, please.
I have one question. Dear Felix, firstly, thank you very much for the very interesting presentation. In fact, I'm also interested in meshless Lagrangian methods of in CFD and computational fluid dynamics. So I have some questions to your method, related to your method. First of all, yes. Can you tell me, are the particles associated with masses? So I mean, do you consider material particles or no?
No. No. In this method, the particles are only interpolation points. So they don't carry mass in that sense, but they carry all the properties of the fluid, as the velocities, pressures, and temperatures.
Thank you very much. And the other question, for example, just for me, it's I'm very interested in simulating flows, maybe more simple flows comparing to your case. But what about applying your method to estimating hydrodynamic loads acting on the on structures? So is it possible to use your method in order just to simulate the flow around some structures and to estimate hydrodynamic loads?
Yes. For example, during the validation of this method, I also considered free surface flows interacting with structures. For example, the dam break problem with some obstacles. And they were modeled correctly. So I think yes, you can use this formulation to
and as I understand, it is of course it is possible to solve easily problems of these in the hydroelastic state, taking into account hydroelastic phenomena. Yeah, when the structure is deformable or movable due to acting hydrodynamic loads. Yes.
Yes.
So there are no constraints about moving boundaries and so on. So we can easily simulate moving problems with moving boundaries, with moving solid boundaries, or with deformable boundaries and so on. Yeah.
Yes. It is easily.
Thank you. Thank you again. Very interesting. This method seems to be very interesting for me. Maybe if it is possible, we can discuss it in more details, maybe after the seminar. Thank you.
Yes, it is, sure. Thank you. Also.
More questions, please.
Can I ask the question also?
Tatiana, please.
Yes, Felix, please. It's also the question about the solidification problem with rectangular cavity. What are the velocities of the flow? It seems to me that they are not very big. Can you tell me the Grashof number, for example?
The Grashof.
Approximately.
I have no.
You don't know, but I'd like to say that if you will increase the difference between the temperatures in your left boundary and right boundary, you may have the more strong velocities. And how you your method will work for the situation with stronger velocities. What will be the time step you must it will be the problem more complicated that solved here.
Yes. I think I capped your idea. Yes, here in this example, the differences between these two temperatures, as I remember, was 2 degrees, and the melting and the melting temperature was in the middle of this interval. So yes, the differences here is small. So the velocity in the cavity is small, but yes, when you if you increase the temperatures in the walls, the velocity will increase, and yes, it will be needed to decrease the time step because we are solving. I can go back to the formulation. We are solving the position of the particles through first order of accuracy equation here. So as you can see here, we take the past position of the particle, and then with the current, with the past velocity, we update the particle position. So if we have exactly the same time step, this position could be incorrect. So yes, we will need to decrease this time step in this case. But also we can use some other approaches to update the particle position, so we can increase a little bit the lower or the upper boundary of this time step, and it will be a little bit bigger.
So I think that it will be interesting to check your method for the problems with greater velocities and to compare it with other methods that exist for incomparable flow simulations.
Yes, that is true, and this is a really good observation and idea. I will take it for validation also.
Thank you.
Thank you very much.
Colleagues, do you have more questions?
May I ask a question?
Yes,
Yes.
please.
First of all, I would also like to thank Mr. Saucedo for a very interesting presentation. But I just didn't quite a bit understand about Meshfree method. So I understood that it is called Meshfree because basically you found a way to interpolate all values of the sort functions with this neighborhood.
Oh yes.
So this is why it's Meshfree.
Yes, this is because it is Meshfree because you don't need the sense of these meshes to solve the governing equation. So you only need the position of the nodes, and with these positions in the nodes, you interpolate the variables, taking into account the constraints of the physical equations. But you don't need to construct these meshes with predefined relationships between the nodes. So the nodes can evolve in time without any constraint. So by that reason, they are called mesh-free or meshless methods.
So this radius of a neighborhood is how is it chosen?
You only need to have enough equations to complete the linear system. For example, if we have a 2D problem, we need to compute, for example, here the pressure. We need to compute two first spatial derivatives, and we need to compute three second order spatial derivatives. So in total, we have 6 unknowns in this equation. So we need to have at least 6 equations. So we choose the size of the neighborhood, assuming that we will have at least six particles in the neighborhood. Usually you select this with this smoothing length. So the smoothing length is approximately 3 times the mean distance between all the particles in the domain. So you calculate the mean distance between particles, and then the smoothing length is 3 times this size, and this neighbor size always assure that you will have this number of particles in your domain.
Thank you.
You're welcome.
Colleagues, maybe more questions?
Yes, and may I ask one more question, or maybe even 2 more questions? First of all, it's connected with the problem when you simulate the flow, when you simulate the particles, when you just calculate some properties on the particles which are placed close to the free boundary, free surface, yeah?
Yes.
And in this case, this, I should say, closure zone, neighboring zone, one part of this zone is, for example, this is a water phase, yes, and the other, or it's, sorry, and the other is, for example, ear. And how this technique works, I mean, technique of expanding into series and Taylor expansions when we have significantly different properties of 2 media.
Oh, okay. Yes, when you have differences between the properties, for example, this occurs during the solidification. During the solidification, we have a mushy zone that is like the transition between a liquid material and solid material. So here we have a deep change, for example, in the viscosity. And also we have a little change in the density. For example, the little change in the density is not too critical, but the deep change in the viscosity is something that you need to take into account. In this case, this equation, I will go back a little bit. This equation that we have here, the Navier-Stokes equation in Lagrangian form, is not the correct form for that problem, because here...
Yes, absolutely, because viscosity coefficient is not constant in this.
Yes.
Yeah, I understand.
Yes, so here you need to consider the Cauchy conservation equation, and you model exactly the same, but with that equation, not the Navier-Stokes equation. You take the Cauchy equation, taking into account the change in the viscosity. The numerics go well, but you need to control also the error in the simulation throughout the time step. So this is the only
okay, and what about, for example, simulation of some liquid, for example, just a water with free surface, for example, with waves on free surface and so on. When there is a free boundary, and how can we apply the expansions you have shown on some previous, or maybe in the next slide? I mean, when you how to introduce the neighboring zone, this closer zone, because only, for example, 1/2 of this zone will be in liquid region and flow region, and the other part will be in some other region. Yeah, for example, if we just imagine the diameter of this zone, below it will be water, and above it will be air.
Yes. Yes, in these cases, for example, when we are in an interface between two zones, that is a good observation. For example, in first, this neighborhood maybe won't have these 6 particles needed to compute everything. So you need to increase the size of the neighborhood to cap more particles. So you can
Okay,
add this.
So as I understand, we do not consider strong discontinuities between properties, and because of using these I should say smoother functions, yes, these exponential functions, we just smooth somehow
Yes.
the properties, and to consider some, I should say, some transition zone, in fact.
Yes.
Mm-hmm,
Yes,
mm-hmm.
yes. You consider some adaptativity of.
Yeah, yeah. And maybe my last question: when you consider movements of particles, sometimes, as I know, in the methods of such kind, sometimes we obtain that in some regions there are a very small number of particles.
Yes.
As I understand, you maybe introduce somehow some new particles in order to avoid such voids, I should say. Yeah.
Yes. Yes.
How you solve this problem?
Yes, this is a geometrical problem. As you say, we can have a zone with a coarse number of particles, but we have also some zones with a fine number of particles. So you can always delete, for example, particles with a interpolation, a part interpolation between the properties. So you assure that the particles you eliminate from the domain is not lost. You consider this information in the closer neighbors. And in the opposite case, when you have a hole in the domain, you can always add with geometrical algorithms, for example, a triangulation algorithm. You can always add new particles, and you also interpolate the new information of this particle with the information of the neighbors.
And Felix, have you heard about the so-called particles FEM, particles finite element method, which is been developed by scientists from Spain and from Argentina?
Yes.
Eugenio Onate, Sergio Idelson, maybe you know that. I think your method is more or less close to the method, maybe not in details, but some basic principles are more or less the same, as I understand, yes?
Yes, that is true. I have read some works from this PFM method, and yes, they are related. They have some differences. For example, the PFM method could be called some generalized finite element method. And
yes, I understand. Of course, I understand that the main principle, the main idea of how to solve equation about pressure is in your method is very different from PFM, but just some general idea, I should say. I think it's more or less the same.
Yes, that is true. Yes, they are.
Thank you very much. Thank you.
You're welcome. Thank you.
Felix, thank you for your presentation. And now maybe we can discuss how to cooperate or how to collaborate in next 1 year, 2 years, or maybe few years. Dear colleagues, do you have any ideas how to collaborate or cooperate with Felix?
Maybe in this connection, I have also a question.
Okay, yes.
One more question, not quite a general question. So you showed us that this method is very good, but why we should, after this presentation of this method, ever use other methods? So what are, you have shown benefits, but what are drawbacks of your method? What are limitations? So maybe it's about approximation, because anyway, it is approximation. And if you compare it with other methods, other approaches, what is, so what if you compare it to other approaches, when it's better to use this method and when it may be better to use more conventional traditional methods.
Okay, yes. Yes, as this is a Lagrangian method, a Lagrangian formulation, this method will be always better than mesh-based methods when you have high deformations in the computational domain, or for example, when you have fragmentation of the computational domain. This method will always be a good candidate, or maybe in sometimes the best candidate to model this kind of problems with this method, because for example, finite element method is based on solid mechanics where the elements cannot fragment. So we can say that the traditional mesh-based methods are not or were not developed to deal with that kind of problem. So in these cases where you have high deformations, fragmentations, sloshings, sprayments, this method will work correctly. Of course, if you have not this behavior in your problem, maybe mesh-based methods or some traditional methods will work better, because they were specifically developed to deal with that kind of problem. So this will be like the two differences between what method to use in what kind of problem. So we can yes, put mesh-based methods in for problems where you have no high deformations or fragmentations or this kind of issues, and you can put Meshfree methods, my method, finite pointed methods in the category of high deformations, fragmentations, sprayments, atomizations. So this will be the idea, for example, on how to decide between these two families of methods.
Thank you.
You're welcome.
I, as a chair of seminar, I can propose at least two ways for collaboration. First of all, I would like to invite you, Felix,
yes.
to participate in our annual conference, which will take part on the first week of December in Moscow.
Yes, yes.
Please try to find time for 3 or 4 days in Moscow.
Yes,
I think you will find many people who will appreciate your work and who can discuss some features of meshless methods with you. As a second step, I can propose maybe to run some model cases for trivial flows like a backward step or maybe droplets interaction, just to see how your method behaves in comparison with traditional mesh methods. And maybe my colleagues can propose other ways of collaboration. Maybe Ilya, can you say about possible future collaboration?
Yes, I think as you understand from my questions, I'm very interested in this method. Seems to be very interesting, and I think it's a good idea maybe to discuss it in more details and maybe to yes, to compare some approaches, different approaches, to understand maybe a little bit better in which problems some methods are suitable, your methods, maybe our methods will be also interesting for you. Maybe it is possible to find some common points, I should say, and some approaches which can be useful in different methods, but which make it possible to improve our researches. I think it's very interesting idea to collaborate somehow, to maybe to understand ideas, to understand problems which can be solved by using such methods and so on. For me, it's really very interesting.
Thank you. Yes, I agree with you.
Okay, thank you.
And another one idea, maybe if you participate in other conferences, maybe we can find some common conferences where our colleagues will participate, and then we can meet on these conferences.
Yes. I think this is also a good idea. Maybe if we, I don't know, share our calendar, we can see where we will be, and we can try to coincide in these conferences.
Yes, but I'm afraid we cannot be sure just now when there will be some conferences because of coronavirus problems. So I think maybe not earlier than after half a year. I think maybe in very end of this year, or even on the next year.
Yes, that is correct. Yes, there is no security about the end of the semester. Yes.
Also, Felix, do you know about maybe joint grants between Mexico and Russia? Because I looked sometimes for such grants, international grants, but unfortunately with Mexico, I didn't find many possibilities. Actually, I like very much Mexico. I fui en México unos veces. Fui, por ejemplo, in Puebla, in Universidad Autónoma de Puebla, and you can see a picture during the Dia de los Muertos, Day of the Dead.
Oh, yes.
Celebration in November, maybe. So,
yes.
Yo fui en Guadalajara, in Universidad de Guadalajara, Sinvestav. You know Sinvestav in Mexico.
Yes, I know. This is one of the best.
Estudios avanzados de Instituto Politécnico Nacional.
Yes.
Yes. So, and in Universidad UDG, Universidad Guadalajara, I collaborated with Professor Padjarov from, originally from Russia.
I see.
So it would be a very good idea to find some grants, some possibility for collaboration. So, but unfortunately, with Europe, we have sometimes international grants, but with Mexico, I hope they will appear, but I don't know if you know something about that.
Yes. Well, maybe we can try also to find some funding. I don't know, for some topic specifically. For example, some of these points, for example, run more benchmark cases with this method. That was one proposal could be funded by the CONACYT here in Mexico. So we can get some funding, not a lot of funding, but we can, I don't know, fund some visits, fund some materials to the developing, and we can at least start with this kind of possibilities. And yes, when we have an opportunity to have a joint project between the two countries, I think it will be really good. But the first step we can do if this is not available is, I think, in this way, and also in this way we can show that we are developing a collaboration relationship. So it will be also easier to get these big fundings between the two countries when they appear. I don't know if you capture my idea.
And also to the words, I want to add to the Matvey's, what Matvey told you about the conference. If
Yes.
you come to this conference, you also will enjoy a very rich cultural program. So usually after the last day of the conference, you visit Kremlin, other interesting places. And also you can meet many specialists on computational fluid dynamics during one day of the conference, and in general on informational technologies also. So I think that you will find it very interesting.
Yes. I always wanted to go to Russia, but I needed a visa to go there, so I wasn't able to go, but yes, this is something I want to do. Indeed, I also try to learn Russian here in Mexico, but I completely forgot everything. Maybe the written Russia I can more or less remember, but not anymore. I went only to Bulgaria, and I used some of the Russian there when I was younger. But yes, this will be an opportunity to know these cultural treasures from your country.
Felix, thank you
Just,
again for your talk. I think we discussed a lot of ideas, and I think we have some common points. We can continue our discussions via email, or maybe
yes,
we
sure.
can organize another one meeting using Zoom, for example, with Ilya, and maybe we will come to some fruitful collaboration. Thank you.
Yes, thank you to you also by this opportunity, and also by let me give this talk to all of you, and by your time. Yes, thank you very much.
Colleagues, our seminar is over. Thank you for participation. Bye.
Thank you.
Thank you.
Félix, muchas gracias. Fue muy interesante.
Muchas gracias por tu atención. Gracias.
También tenemos aquí Jackson de Barcelona. From Barcelona, maybe he's from Spain and originally from Bolivia. Maybe Jackson knows something. Jackson, are you here?
Hi, Elias. Hi, on the team of ISP RAS. I'm still in Barcelona. Do you hear me?
Yes, I can hear you.
Sí. Thank you very much for the invitation, Elias. I can say hello to all the team of ISP RAS, Matvey, Elias, Sergey, Victoria, Daria, and I think also you did a good presentation and good topics about particles, because I am here in Barcelona, and also I was in some presentation of particles with the team of SIMNE, because
yes.
I am here in the Institute of Lumen, that we are partners of SIMNE, and also they are working in this topic, not only in the hydraulics structures, especially with sediments. They mix the particles with the multi-phase flow, and they mix these two equations.
Oh, I see.
You are welcome to Barcelona also.
Thank you very much.
También podemos hablar español.
Sí, yo creo que sí. No, pues muchas gracias por atender a la presentación, Jackson.
No, gracias a ti. Okay, thank you.